Welcome to the deep dive. Today, we're going to be tackling computer networks. It's one of those topics that can feel like a secret handshake, in the tech world. But don't worry, we're going to break down the jargon and get you feeling confident about what's actually happening when you send an email or hop onto a video call.
That's right. We're going deep with a university-level course document on computer networking. It's a bit dense, but we're here to pull out those golden nuggets for you.
Perfect. Okay, so first things first. What actually is a computer network? It seems obvious, but I'm willing to bet there's more to it than meets the eye.
Absolutely. The textbook definition will tell you it's about connecting computers for communication and resource sharing. But think about it this way. A single supercomputer, even a powerful one, has its limits. A network lets us pool resources and work together in ways that were impossible before.
So it's kind of like the difference between a solo musician and a whole orchestra. Each instrument can make beautiful music on its own, but together, they create something much richer and more complex.
I like that. It's about synergy. Take the SETI at Home project, for example. It uses a distributed network of computers to analyze data from space, searching for signs of extraterrestrial life. A single computer would take centuries to process that much data, but by spreading the work across a network, they can make much faster progress.
That's amazing. So it's not just about saving money on printers.
Yeah.
It's about tackling huge, complex problems that would be impossible otherwise.
Yeah.
Okay, so we've got this idea of computers working together, but networks come in different flavors, right? Like my home Wi-Fi feels different from, say, the entire internet.
You're right to notice that distinction. Networks exist on a scale from a personal area network, or PAN, which might just be your phone connecting to your smartwatch, to the global reach of the internet, which is a WAN, or wide area network.
My home Wi-Fi, that's a LAN, a local area network. It's just for my devices within a small area.
Exactly. And each type of network has its own characteristics and purpose. A LAN is great for sharing files and resources within a home or office, while a WAN, like the internet, is designed to connect networks across continents, sharing information and resources on a global scale.
And somewhere in between, we have those MANs, metropolitan area networks you mentioned earlier.
Yes. Think about a city government needing to connect all its departments and buildings across a wide area. That's where a MAN would be ideal.
Okay. So we've got our network types, but I'm curious, how do they actually work? Is it just a free-for-all of data flying around, or is there some order to the chaos?
Great question. That's where network models come in. They provide a framework for understanding how data flows and how devices interact. Two common models are peer-to-peer and client-server.
I've heard those terms before, but never really grasped the difference. Is it like direct messaging versus posting on a public forum?
You're on the right track. In a peer-to-peer network, each device acts as both a client and a server, sharing resources directly with other devices. Think of it like a group of friends sharing music files directly with each other. There's no central authority controlling the flow of information.
So it's very decentralized. But what about client-server? That sounds more like the internet to me.
It is. In a client-server model, you have a central server. Think of it as a powerful computer that manages resources and provides services to the clients, which are the individual computers or devices. When you access a website, you're acting as a client, sending a request to a server that hosts the website.
So server is like a giant library, and the clients are the patrons requesting books. But doesn't that make the server a potential bottleneck? What happens if it crashes?
That's a great point. The server is a critical component in a client-server network, and its reliability is crucial. That's why redundancy and backup systems are essential. They ensure that if one server fails, another can take over seamlessly, minimizing disruption.
That makes sense.
Yeah.
So we've got different types of networks and different ways they can be organized. But how does data actually travel through all this? I mean, it's not like little envelopes are whizzing through cables, right?
Right. We need to zoom in even further and talk about how data is broken down and transmitted across the network. This is where we encounter a model called the OSI model, which stands for Open Systems Interconnection.
Ah, yes, the OSI model. It's one of those terms that always sounded intimidating, like something only network engineers need to worry about.
It can seem complex, but it's actually a brilliant way to break down a complex process into manageable chunks. Think of it this way when you send an email. A lot happens behind the scenes to get that message from your computer to your recipient's inbox. The OSI model helps us understand the different stages of that journey.
Okay, I'm intrigued. So instead of getting lost in the technical details, can we walk through a real-world example? Like, how does the OSI model apply to sending an email?
Absolutely. Let's say you're sending an email to a friend. The OSI model breaks down that process into 7 layers, each with a specific job. It starts with the application layer, where you compose your email in your email client. This layer is all about the user interface and making sure the data is formatted correctly for the application you're using.
So that's where I type my message, add attachments,
Yeah.
and hit send. But then how does it actually get out of my computer?
Right. That's where the next layer comes in, the
Yeah.
presentation layer. It's like a translator, making sure the data is in a format that can be understood by the network. It handles things like encryption and compression.
So it's making sure my email can be read by my friend's email client, whether they're using a different operating system or a different type of device.
Exactly. Then we move to the session layer, which manages the connection between your computer and your friend's computer. It's like setting up a phone call. It establishes the connection, keeps track of who's talking, and makes sure the conversation flows smoothly.
Okay, so we've got the message prepped and the connection established. But how does the actual data travel through the network?
That's where the transport layer comes in. It's responsible for breaking down the data into smaller packets, adding addresses and error-checking information, and making sure those packets arrive at their destination in the correct order.
Packets. So it's not sending the entire email as one big chunk of data?
Nope. It's more efficient to break it down into smaller pieces that can be sent independently. Think of it like sending a jigsaw puzzle through the mail. You send each piece separately, and then the recipient reassembles them at the other end.
Ah, that makes sense. So the transport layer is like a puzzle master,
Yeah.
carefully organizing the pieces and making sure they all reach their destination.
Precisely. Then we move down to the network layer, which handles the logical addressing and routing of those packets. It figures out the best path for the data to take through the network, kind of like a GPS for data packets.
So this layer is responsible for making sure my email doesn't accidentally end up in someone else's inbox.
Exactly. It uses IP addresses, which are like unique identifiers for devices on the network, to ensure that the data gets delivered to the right destination.
This is starting to feel like a well-coordinated relay race, each layer passing the baton to the next.
That's a great analogy. And finally, we reach the last 2 layers, the data link layer and the physical layer. The data link layer is responsible for error detection and correction, ensuring that the data is transmitted reliably across the physical medium, whether it's a wired or wireless connection. And the physical layer is all about the hardware, the cables, connectors, and signals that physically transmit the data bits.
Wow. So it goes all the way from the abstract world of software down to the nuts and bolts of hardware. But why do we need this model? It seems like a lot of complexity for sending an email.
It might seem complicated, but this layered approach is incredibly powerful. It allows different devices and systems to communicate seamlessly, regardless of their underlying hardware or software. It's like having a universal translator for computer networks.
So, by following these standards, any device can talk to any other device, regardless of who made it or what operating system it's running.
Exactly. And it allows manufacturers to focus on their specific areas of expertise, knowing that their devices will be able to communicate with other devices that adhere to the same standards.
That's amazing. I never realized how much thought and coordination goes into making sure all these devices can talk to each other. So the OSI model is like a common language for computer networks. Is that why we hear so much about protocols and standards in the tech world?
You got it. Protocols are essentially sets of rules that govern how devices communicate. They define everything from the format of data packets to the procedures for error handling and connection management.
So protocols are like the traffic laws of the internet, making sure data flows smoothly and safely.
Perfect analogy. Without protocols, it would be chaos. Imagine a world where every car manufacturer had its own traffic lights and road signs. No one would know what to do.
Right. It would be impossible to drive anywhere. So these protocols are what allow all these different devices to work together in harmony.
Exactly. They ensure interoperability and allow for innovation. Companies can develop new technologies, knowing that they'll be able to integrate seamlessly with existing systems as long as they adhere to the established protocols.
Okay. So protocols are the rules of the road.
Yeah.
But who's making those rules? Is there like a global council of network overlords deciding how everything works?
Not exactly overlords, but there are organizations that play a key role in developing and maintaining these standards. One of the most well-known is the Institute of Electrical and Electronics Engineers, or IE. They're responsible for a wide range of technology standards, including Ethernet and Wi-Fi.
Ethernet and Wi-Fi. Those are terms I definitely recognize. So thanks to the IE, we can connect our devices without worrying about whether they'll be compatible.
Exactly. Another important organization is the International Organization for Standardization, or ISO. They develop standards for a wide range of industries and facilitate international trade.
So it's not just about making sure my phone can connect to my Wi-Fi. It's about creating a global ecosystem where devices and systems can work together seamlessly, no matter where they're made or who's using them.
Precisely. It's about creating a level playing field and fostering innovation. And then there's the Internet Engineering Task Force, or IETF, which focuses specifically on Internet standards. They're the ones responsible for protocols like TCP/IP, which are the foundation of the modern Internet.
So between the IISIE and IETF, they've pretty much got the entire network world covered.
You could say that. They work together, along with other organizations and industry experts, to ensure that the Internet and other computer networks continue to evolve and meet the growing demands of our digital world.
It's amazing how much collaboration and coordination goes on behind the scenes. But all this talk about protocols and standards makes me think about the flip side. Security. With all this data flying around, how do we keep it safe from prying eyes and malicious actors?
It's definitely a valid concern, but the good news is there are tons of brilliant people working on network security. It's a constantly evolving field. Because as technology advances, so do the threats.
So it's like an arms race. The good guys versus the bad guys.
Yeah.
Always trying to outsmart each other.
In a way, yes. But instead of weapons, we're talking about firewalls, intrusion detection systems, and encryption algorithms, all these tools designed to protect our data and keep networks secure.
Okay, let's break it down. What's a firewall? Exactly. I've heard the term, but I picture a literal wall of fire blocking hackers, which can't be right.
It's a more abstract kind of fire. A firewall acts as a barrier between your network and the outside world, controlling the flow of traffic based on predefined rules. It's like a security guard at the entrance to your network, checking IDs and only allowing authorized personnel to enter.
So it can block suspicious connections or prevent unauthorized access to sensitive data?
Exactly. And then you have intrusion detection systems, which are like security cameras for your network. They monitor activity for any signs of malicious behavior and alert administrators if anything suspicious is detected.
That's reassuring. So it's not just about keeping bad guys out. It's also about being able to spot them if they manage to sneak in.
Absolutely. And then there's encryption, which is one of the most powerful tools in the security arsenal. It's like scrambling your data so that only authorized users with the right key can decipher it.
So even if someone intercepts my email, it's just gibberish to them unless they have the decryption key.
Precisely. Encryption is used everywhere, from securing online transactions to protecting sensitive information stored in the cloud.
That makes me feel a lot better about online banking and shopping. But with all these sophisticated security measures, are networks truly unhackable? I still hear about data breaches and cyber attacks all the time.
Unfortunately, no system is 100% foolproof. Hackers are constantly finding new ways to exploit vulnerabilities, so it's an ongoing battle to stay ahead of them. But a multi-layered approach to security, combining strong passwords, firewalls, intrusion detection systems, encryption, and ongoing security audits, can significantly reduce the risk of a successful attack.
So it's like a castle. You need multiple layers of defense to deter potential invaders.
Yeah.
Firewalls, a moat, vigilant guards, and maybe even a dragon or two just in case.
That's a great way to think about it. And just as castles were constantly being improved and fortified, network security is a constantly evolving field.
So it's not a set it and forget it kind of thing. You have to stay vigilant and adapt to new threats as they emerge.
Absolutely. Awareness and education are crucial. Everyone who uses a computer network, from individuals to large organizations, needs to understand the importance of security best practices, like using strong passwords, keeping software up to date, and being cautious about suspicious emails or links.
That's a great point. It's not just about the technology. It's about people being smart and responsible. Okay. We've covered a lot of ground in this deep dive. We've explored the basic building blocks